Okay, let's get started. So in this last thing, I'll cover two things: mixers and amplifiers. More on the amplifier noise, like how to think about noise and amplifiers. So we have discussed mixers briefly earlier when we were actually talking about these 90-degree hybrids, because they are an essential component in certain types of mixers. But we just look at what the mixer actually is. And again, there are many different ways of constructing it. But essentially, we talked about the fact that mixers allow you to multiply signals, right? And for that, you need some nonlinear element in it. Essentially something, because if you send two signals in a linear system, what you get is just the sum of them, right? That's basically the superposition principle. So that's very important for signals to not get distorted when you are sending many different things on the same transmission line. But if you want to specifically do an operation like multiplication, it's a nonlinear operation, and that requires some device which is nonlinear. So it's typically a diode for mixers. Sometimes transistors are also used. Okay, so the essential operating picture of a mixer is shown in this figure, and there are two standard ways in which it operates. It's a 3-port device typically, which has what is called the LO port, which is here. LO stands for local oscillator. Then there is the IF port, where I stands for intermediate and F stands for frequency. It's intermediate frequency. You'll see why it is called intermediate frequency. And then the output in the top case is called the RF port. Okay, it's just they were not being very intuitive about this. And in this, the top figure, it is usually or it's drawn in what we call as an up conversion mode. Okay, what this means is that LO and IF are the inputs, and at the output, so remember these are written in terms of frequencies. So the output frequency you will get at the RF port is LO plus and minus of the IF. This comes from the fact that the mixer is actually multiplying the signals at LO and RF. So if you consider them as sine omega 1t and sine omega 2t, if you multiply sine omega 1 into sine omega 2 from the trigonometric identity, you know that it will create a term which is proportional to omega 1, or has a frequency omega 1 plus omega 2 and a frequency omega 1 minus omega 2. So that is basically, so if omega 1 is LO and omega 2 is IF, that's what you get. You get omega 1 plus minus omega 2. Okay, so that's what's shown here. Is the IF frequency is usually the lowest frequency in the problem. So that's the IF frequency here on this frequency graph. LO is here. And then at the RF, you get these two. These are also called upper and lower sidebands of this thing. So this mode of operation is called up conversion. The reason it's called up conversion is that essentially the information which is contained in this IF signal is transferred to these two sidebands. Now, you have seen this probably even in high school in the context of AM modulation, right? This actually is nothing but AM modulation, because what does multiplication mean? You have one term multiplying other, which can equally say that one of the frequencies is acting like the amplitude of the other frequency term, right? Even though when you talk about AM modulation, there's something called modulation index. It's like 1 plus some small quantity, which tells you how much modulation is happening. But that also comes in here. But effectively, that is what is happening. And then you can think of this output signal, which has this plus and minus IF as the amplitude modulated signal. So the LO is amplitude modulated by the IF signal, which is the same as saying that they are getting multiplied. Okay. This is just from the AM example. It's a very common thing to do this. This idea that the information contained in this thing is exactly transferred to the sidebands is what allows radio transmission to work. You take your audio, which is basically your IF frequency for AM, and then you multiply it by a high frequency signal, which is often called the carrier wave, which is the local oscillator here. And then you get the same audio content now moved to a frequency near the LO frequency, right? So the LO frequency is basically the radio station frequency. So when you tune to that frequency, now for AM, everything is actually in low frequency because the AM stations are in, kilohertz and or hundreds of kilohertz. FM is 100 megahertz, right? But that is a slightly different kind of modulation. It's phase modulation or frequency modulation. But for that also, you need some kind of nonlinear system only. But the point is that now the 20 kilohertz audio information has been moved from 20 kilohertz up to some higher frequency, which can then be transmitted more easily. And then you can recover that. And in fact, this recovering operation is exactly the opposite thing which is shown in the bottom thing, is the down conversion operation, where the inputs are LO and RF. So this basically tells you that the LO is always an input signal. That means you are providing that signal. And now the RF is the input signal and the IF is the output signal. The mixer actually still does exactly the same operation. It multiplies LO and RF. And again, you create sums and differences. But now, because the RF frequency is typically very close to the LO frequency, the sums and differences are not close to each other like in this case. So see here, the LO is the high frequency and IF is the low frequency. So LO plus IF and LO minus IF are all close to each other. Okay. But in this case, you have LO and RF close to each other, and the difference is at much lower frequency, and the sum is at much higher frequency. In most typical cases, the sum is actually not even passed through because the analog response of the mixer naturally has a low pass filter in it. But otherwise, you usually put a low pass filter because in the down conversion mode, it's the low frequency part of the signal which you are interested in. The information contained in the high frequency is also exactly identical, just like it was there. But you don't worry about it. It's the same duplicate information. So you worry about the low frequency part. So if you do these two operations back to back, then essentially you take in LO, you have IF, you have LO plus minus IF, then that goes into the RF port of the second mixer and then comes back again as IF at the low frequency. So you can recover the IF part. So this full, both these operations are done by the same device, and they essentially multiplies the signals you give it in. So it doesn't matter whether the input is on the RF or the IF. The other port which is left over will contain the product with some filtering. So when you do the down conversion mode, IF will only give you the down converted frequency, the difference frequency, because the sum frequency is too high to pass through. And in many cases, it's intentionally rejected out because you're not interested in this.
Why you need to detect the signal to the low frequency?
So if you want to listen to your radio, that's what your radio actually does. So the radio station does the up conversion operation. Your radio at your home does the down conversion operation so that you can come back, you can get an electrical signal which is the same as the audio frequency signal. So then you can hear it, right? So this, that's an example specific for say audio transmission, but this is the same for even video transmission, right? So video signals are not in tens of kilohertz, they are in megahertz. But when they are also transmitted over antenna, they are modulated on a much higher frequency carrier wave. The reason you do that is that higher frequency waves can be propagated easily over long distances. But then you have to bring it back to the usable regime, because you cannot directly hear 100 megahertz. So the information is contained in a very small range of frequencies around 100 megahertz. So you bring it back and then you put it through a regular speaker. That's what.
We can use the method to extract RF signal, extract the data from RF signal to DC. I mean, we can vary that local oscillator frequency, and that will match at any particular frequency, I think, in the RF. Let's say in the RF, there is a band of signal, and we vary the oscillator signal.
Yeah.
Then we will have some DC part also in the output, right?
So the DC part is basically part of the IF. So whether you get a DC signal or not,
No, I mean,
after down conversion.
Yes, sir. I mean, from the DC signal, we can measure the what is the RF signal is there, right?
But why are you calling it only DC? It's not.
No.
Usually any signal with any information will have more than one frequency in it. Otherwise, it has
more than one frequency. But if we are interested in a particular one frequency, then we can extract the data at that particular frequency from that.
But what data will you extract? For if you only had one, so okay, this is actually a point which is important to remember. I think I mentioned this some lectures ago also. When you say one frequency, you have to strictly mean one frequency. Okay. You can only have one frequency if your signal is infinite in time. Otherwise, there is always going to be a band of frequencies. Any information means there is some function varying as a function of time. And that will have a finite bandwidth. So for example, if I'm speaking to you right now, all the information I'm sending is contained within maybe a few hundred hertz, around 500 hertz. Okay. So if I only send 500 hertz out of that, you're not going to make out anything. It's always changes. The change is basically what the information is. If you have only one frequency, you have only one thing you can send, the amplitude and the phase. But the moment you say that, okay, I'm going to now change the amplitude, that automatically means that there is a finite bandwidth to it, because you have to specify how quickly you're going to change. Okay.
But I think still we can measure something. I mean, the area.
I'm not sure what you're asking actually. What is you're repeating the same thing what I'm saying, but you're not.
No, I will ask you after that.
Okay. Yeah.
We use down conversion in a multiple system. We send IF frequency to one port, and the same IF signal can be sent to the other mixer, or we send IF frequency separately all the other mixers, the multiple mixers.
No, I mean, that depends on what you're trying to do. Here, I'm just right now only telling you that the same mixer can do both up conversion and down conversion depending on what ports you're exciting it. So up and down here basically means where the information is changing in frequency space. Up means it's going from low frequency to high frequency. What is going? It's the information contained in the IF, which is getting up converted to around LO frequency. So this is the up part. Similarly here, the information in the RF is being down converted. So this is the down part. Okay. So typically FLO is similar to FRF, and it's much, much greater than FIF. Okay. This is the standard configuration for most mixers. It's not always true. Some of these bands can overlap. Sometimes IF frequencies can go all the way up to RF frequencies, but usually IF frequency is much smaller, and LO and RF is the high frequency part of the system. So if you want to transmit information like in a radio station and you are up converting, then you have to have a down conversion stage at a later point to recover that information which was sent. You can send the same IF to multiple mixers if you want, but the question is, what are you trying to do? Right? Multiple mixer setup doesn't mean anything by itself unless you specify what is it you're trying to do there. Okay. So this is essentially the basic operation. So here it says the output of the idealized mixer is basically that now here output is being treated as the RF port. It's basically some constant K multiplied by the LO frequency, sorry, LO term and the IF term, which is just cos written as some sinusoidal function. And that gives you the difference and the sum, which is basically what we are saying. So again, nomenclature I mentioned, the LO plus is called the upper sideband, the LO minus IF is called the lower sideband.
Yeah, LO should have a very narrow bandwidth. Right?
So LO is by definition, I mean, in the ideal case, is like a delta function. So in a real setup, the line width of that will depend on what source you're using, but ideally it has a very, very sharp narrow line. So it's like your laser in an optical system, if you want to think about that. So microwave sources can generate signals which are very, very narrow in band. So that is sort of a given. It's not critical for it to be very narrow. It really depends on how accurately you want the amplitude and the phase to be recorded. Essentially, it'll add like a noise to the system. So the one way to think about it is that an LO which is not narrowband or which is not precisely one frequency can be modeled as a perfect LO which is modulated in amplitude or phase by some small frequency, and that gives you is a bandwidth. So now this extra modulation can be thought of as an unwanted signal in your actual spectrum, because you are also sending an IF which has some frequency band, but the LO has a natural line width, which means that it will have some components very close to its frequency, and that will be a low frequency noise in your output. But you can, if your information is not at very low frequencies, then you can reject it out by just filtering it and then saying that, okay, if you say that I'm only sending audio between 100 hertz and 10 kilohertz, I can filter that out. And all the noise, the unwanted part will be, say, less than 10 hertz, for example, if that's the line width of the LO. But here we almost always assume the LO as a perfect delta function. The time dependence of the bandwidth will comes on how the amplitude and the phase is varying. So usually LO is a fixed signal. You just turn it on to a certain power and then that's it. You leave it like that. All the changes are happening at the RF and the IF port. So that's essentially the basic mixer. What it actually looks like is, here is an example of a very simple mixer, which is also called a single-ended diode mixers. Okay, this is rarely used in practical design, but it sort of tells you how the nonlinear nature of the diode is actually helping you. Okay, so you first have some kind of a combiner. In fact, here it is drawn as a coupler, so sort of like a directional coupler, where it is combining the RF and the LO into one signal. So these are now basically two frequencies propagating through at this output. So at this point, you have LO and RF both propagating together. So this doesn't mean LO plus RF frequency, right? It's LO frequency and RF frequency. And then this is now being sent to a nonlinear device. So essentially what that means is that the output of this is going to have terms proportional to the square of the voltage you're sending in. So if you have an input signal which has more than one frequency component and you square it, so essentially the point is that you have two signals A and you square it, you get A square, B square, but you also get this term, right? And it's this part which is giving you the multiplication operation. So that's why just a nonlinear, any circuit which has a nonlinear response will create terms like this. And again, these A squares and B squares can be in frequency space, this will be like a term which is sine square omega, but that is also sine 2 omega plus something, right? So that's much higher frequency. So those can be filtered out through these filters, and you only get the term which you're interested in. And in this diagram, it's shown as the down conversion process because the input is RF and the output is IF. So you even low pass filter so that the AB part itself will have, LO plus RF and LO minus RF signals, and this is filtered out, and you only pass the. So there are some other details that this diode has to be biased with the DC signal to put it in the nonlinear regime, and that's why you have a DC bias here. And then there is this inductor, which is called the RF choke. The purpose of this inductor is basically to provide a high impedance path towards the DC bias for the high frequency signals. So it's essentially like a high pass filter. So, a low pass filter. So high frequency signals cannot go into the DC bias. So this is to maintain the impedances in the high frequency regime. And then there are DC blocks on either side. A DC block is just a small capacitor, which blocks very low frequency signals. And this is there to prevent this DC signal from here going into the input and the output circuit. Right. So that's like the simplest form of mixer you can write. In practice, no commercial mixer will be made using this simple design because it creates the nonlinear terms operation actually creates many more terms, and then those are not rejected very well in this particular circuit. So
this coupler is doing A plus B. What exactly is squaring?
The diode. The coupler is just doing A plus B. Yeah, that's just combining. It's the diode which is giving you the square operation, because diode doesn't have a linear IV curve. So you can think of this that the input signal is creating a current in the diode, but the voltage across the diode, which is what is being taken as the output here, is now no longer linearly proportional to I because it's not a resistor. Right. So V is IR for a linear resistor, but for the diode, you're going to have IR, IR square, IR cube, and so on and so on. So there, the square term is what's giving you the useful part. But because there are all these higher order nonlinear terms, right? Because the diode has this exponential kind of IV curve. So all other terms are also there. So they will all create some other frequencies which sort of make this somewhat of a non-ideal. But if you filter things out carefully and work in a very narrow band, then you can also get it to work like a mixer. So this is just there to explain the very basic functionality. You then go to do other kinds of tricks. So a few of them are shown here. So this is called a balanced mixer, where the combination is not being done by a coupler, but like by this 3 dB hybrid or 90-degree hybrid or a 180-degree hybrid. And you now use two diodes. This basically gives you some symmetries which cancel some of the higher order terms, right? Because of the using two diodes. So some higher order terms, because of the fact that you're using a 90-degree hybrid and 180-degree hybrid, they will cancel out. So you can reject some of these unwanted terms using this kind of an idea. I'm not going to go into the detail because this is not something even in practice one ever constructs themselves. But you can build upon this, and you can even have something called double balance mixers or triple balance mixers, which uses more diodes and to create more symmetries to cancel out as many unwanted terms as you can, to give you a fairly clean output, which means that you only get the product of the two frequencies, and all the other kinds of terms are suppressed as much as possible. So I think most commonly used designs are double or triple balance mixers, which use like 4 diodes or 8 diodes in their full design, and they're sort of like a Wheatstone bridge. I think I have a figure here. Let me. See, it's here. So, no, sorry, it was here only. 1 second. So this is a double balance mixer circuit, but this requires these kind of transformers to be designed, because the RF part is connected through this 3 dB 180-degree hybrid, but the LO and the IF are using this kind of a transformer to create excitation on the opposite side of this sort of 4-junction. Looks like this Wheatstone bridge kind of setup, right? So the LO is coupled, and then that biases all the diodes. So the LO is also the power source for this mixer. Basically, it uses to bias the system in the right nonlinear regime. And then the RF is exciting. So you see the LO is going across these two terminals, and the RF is going across these two terminals. So this kind of balancing allows us to cancel out these unwanted terms. And then the IF is actually taken from the same terminal as the LO, because the mixing products are appearing everywhere. And then you put a low pass filter and take the IF output out. So this is the most commonly used circuit. If you look for mixers, you'll see they'll be usually double balanced mixer circuit as well. Okay. So few other things which I wanted to say about the mixer. I think some of this we discussed. I think using this these notes which we have seen before was in the context of the IQ mixer, right? So the conventional mixer is a 3-port device which just multiplies and gives you the output. You can now have a setup like this. Let me see this one. Let's look at this one here. So each of this circle with the cross is a standard 3-port mixer. So you see the L, I, and R marked here. The IQ mixer is a 4-port device which uses 2 3-port mixers which are combined in the following way. The I input of each of the mixer is now called I and Q. Okay, that's for in phase and quadrature phase inputs. The reason for that will become clear in just a second, is because the LO, which is coming here, is split by this 90-degree hybrid splitter, which basically means that if you are sending in sine omega t here, it will create sine omega t and cos omega t at the outputs. So one mixer is being driven by sine omega t. So omega is omega LO here. And the other one is being driven by cos omega t. And then, which means that the I input modulates the sine omega t component, and the Q input modulates the cosine omega t input. And then the two outputs, the two RF ports, are recombined into one signal and sent out of the combined RF port. So there are 4 ports because there is LO, RF as usual, but there are now 2 I inputs called I and Q. And this is the most generic way you can create amplitude and phase modulation of a signal which is LO. Because the most generic signal will have both in phase and quadrature phase components. So the way to now look at the IQ mixer's output is that your RF is going to be I of T. That's whatever signals. Remember that I and Q are low frequency signals, usually going from DC to some finite, into sine omega LO of T plus Q of T cosine omega L. So by choosing I and Q, you can actually create any amplitude or any phase of this signal like omega L. So it gives you more flexibility in terms of doing both amplitude and phase modulations without having to change anything about the by using these two inputs I and Q. So this, in the context of, for example, the kind of things we do, we want to always create microwave frequency pulses which has some amplitude profile. But we also want to control the phase of this oscillation signal. So rather than having to change something on LO, remember I told you LO is always kept as a fixed thing. You can change the phase here by just changing whether I is activated or Q is activated or both are activated. Right? So what does it mean? If, for example, I of t is basically a pulse which looks like this. This is the envelope, right? And sine omega t is basically this high frequency part. If I only send this and don't send this, then I will get a signal whose phase will be matching with this one. If I now send this signal to Q and I don't send anything here, then its phase will be matching to this guy. But I can choose a combination of I and Q in such a way that I square plus Q square root is always the same, because that will essentially maintain the amplitude, this total amplitude at the output. But if I now keep changing I and Q in such a way that the sum square root is constant, but the rest of the values are changing, then you are continuously going from sine to cosine. So you have full control over the phase of the signal as well, of what is coming out. Of course, everything is with respect to some reference, there is no absolute phase which you can define, but you can create a pulse which is proportional to or with this phase followed by a pulse which is at that phase. So this kind of a mixer is very, very useful for generating these kind of pulses. When you are not able to create changes in phase in I and Q itself. Okay. This is only required if you are not able to create a change in phase. But what does the phase of a signal like this actually mean? If this doesn't really have a there's no oscillatory component, but you could do that. Well, I of t now could be some oscillatory signal at low frequencies. So earlier the pulse which I had made, I can call this as a signal whose frequency starts at 0 all the way from DC up to some finite frequency. Right? This is a signal which starts at a slightly higher frequency, but has the same amplitude profile as this. If I use this here, then I don't need the second part, because I can change the phase of this guy from sine to cos, and that will now allow me to modulate this. But the price one pays is that now you have two sidebands. So this earlier this was all at DC, now this is going to have some omega I up here. So the output signal is going to contain omega LO plus minus omega I. So you have to filter out one of those terms if you want to reproduce the same operation here. So that's why doing this is easier in practice, because these I of t and Q of t are usually created by fast pulse generators, or what are also called arbitrary waveform generators. And then they are not usually operating at high enough frequency that you can separate IF and RF. In fact, Gaurav has been working on trying to create a setup where the IF is high enough frequency that without using the second part, you can actually filter out the components. It's more about a practical issue that you have your LO frequency here, and the frequency of interest is here, but this is an unwanted thing. So you have to create a filter which is some kind of a band pass filter that only filters that. So if these frequencies are all very close to each other, then it becomes very difficult to design that filter. You need some very high order filter which are difficult to make. But if you keep these frequencies far enough, then it's easier to filter out one of those things. So, I mean, these are some very specific details when it comes to knowing what kind of equipment you have and what you actually want to do. There are some other aspects to IQ mixers in that this is actually not being the correct output, in the sense that when you send I equal to 0 and Q equal to 0, the output actually should be 0. But it turns out that it's not the case. There is something called an offset LO leakage, which you can model by saying that it's actually something like this. It's I of t plus I offset and Q of T plus Q offset. Which means that I of, when you set I and Q equal to 0, there is still something which comes out at their low frequency. And that what comes out is also frequency dependent. It depends on what LO frequency you're using. Usually we have to calibrate. We have to basically find the combination of I and Q which kills the LO signal leakage at the output. So that usually a DC offset one has to create on these things. So these other uses of the IQ mixer, I think I discussed in the previous lecture, where you can now instead of creating one sideband, both sidebands, it is possible to create a single sideband by sending the IF. So look what's happening here. The I and the Q, which were the two separate inputs, right? Which was, so this I and Q were going to two separate mixers. Now that is actually being created from a single source of IF signal, but using now a 90-degree hybrid to create in-phase and quadrature phase components. Okay, so that actually creates a situation where I of T is now some A sine omega IF T multiplied by sine omega LOT plus the same I cos omega IF into cos omega LOT. What has happened is that the same I is being used to create a sine version of the thing and a phase shifted cos version of the same signal. So this kind of combination will kill one of the sidebands. Usually the upper or the lower sideband, depending on exactly the phases which are used. Right? So this is not the generic case, because you can have a situation like sine AB plus cos BA. That will give you sine A plus B. If you had a minus sign, it will give you sine A minus B, but not the other one. So you can use techniques symmetry. The reason for this is that the previous mixer had 90-degree phase shifted terms going into the two LOs. So by combining it with an IF, which is also 90-degree phase shifted, you can cancel one of the terms and you can leave one of the terms. What effectively this means is that if you start with an IF here and your LO was here, earlier you were getting two sidebands, LO plus IF and LO minus IF, but now you can only get one of them, because the two paths will create opposite signals here, and that will cancel each other out, but it will create in-phase signals at this frequency, and then it will get enhanced. And you can choose which one you select by adjusting the relative phase difference between the two paths. So usually you can buy mixers which do this by design, or you can do it by actually sending the signals in that particular way. So when you buy the mixer, it will tell you which sideband it rejects, whether it's the upper sideband or the lower sideband rejection as well. And all of these work in the reverse direction as well, in the sense that the IQ mixer also can be used in down conversion mode. Here I have been only talking about up conversion, right? Because I and Q are the inputs, LO is the input, and we are looking at the output. But exactly the same thing will happen, because remember, they are still only giving you products, which means if you now send signal at LO and RF, you will now get output at I and Q. But what's the difference between I and Q outputs? The difference is that in one case, the LO, which is being multiplied with the RF, is proportional to sine, and in the other case, it is proportional to cos. And when you actually go through that and you see that if I have a signal at RF, which is some generic sine signal, omega t plus phi, I can write this as A sine phi sine omega t plus A cos phi Sine A cos B plus cos A sin B.
Okay, so then sine cos.
Well, yeah. Sine A cos B plus cos A sin B. So that's sine. Yes, still get the same. 95 cos of. So what this tells you that this signal can be thought of as two quadratures, which are sine omega t and cos omega t, and their amplitudes are proportional to the sine phi and the cosine phi part of the original signal. So the two LOs, which have one proportional to sine and one proportional to cos, they will pick out each of these signals. So what that means is that at the output, the I output will be proportional to this part, and the Q output will be proportional to this part. Which basically means you fully recover the original modulation part, which is the amplitude and the phase. So you can extract the phase from this because you have A cos phi and A sin phi. So from that you can get phi out of that. But if these are all time varying, so for example, if A was A of t and phi was phi of t, then you basically get the time varying response as well. So it's exactly the same process just happening in reverse. And now you get two outputs, which is proportional to the original signal sine component, this part, and the original cos. Why does that happen? Because when you multiply LO and RF, only when you do sine with sine do you get the sine square term. Right? When you do sine and cos, then that when you low pass filter it, that sine and cos alternatively become positive and negative, so they cancel each other out. So that's why only one of the terms shows up here and the other one shows up there. The IQ mixers can be used in this form as well in the demodulation part. Okay. I think that's basically shared now. I don't. Now finish up with this discussion on noise. So the main point of this last discussion is about thinking about noise, particularly of amplifiers. This is of course not specific to microwave frequencies, but this is true in general. And this is this general idea that whenever you have an amplifier, in fact, let me already mentioned this in an earlier lecture. So when we think of an amplifier, we think that okay, there is some signal going in, and some larger signal of the same thing amplified comes up, right? This is what we think when an amplifier is. If we take this diagram very strictly, turns out that this is impossible. What do I mean by strictly? In the sense that what I have drawn here are the only things which are present in your signal at both input and output. Turns out that no amplifier can do this without adding some extra noise on the system. This actually goes all the way down to quantum mechanics. We will not discuss that aspect here. I can send you some reading material on that. But the point is that an amplifier just doesn't take what is at the input, create a larger copy, but it has to add some extra noise. Quantum mechanics tells you that this noise needs to have a certain minimum value. But most amplifiers will be dealing with in commercial, which is available today, do much worse than that. Okay. This noise is much higher than it needs to be as specified by quantum mechanics. So the question is, well, where is this noise coming from? It's coming from the internal circuitry of the amplifier. That's the picture. Now, depending on how the amplifier is designed, this noise could be higher or lower, and that's actually there's a quantity which is specifying how good or bad this is. And the definitions we are going to see is essentially to understand how this is represented in typical microwave frequency amplifiers. Okay. So this property is often called the noise temperature of the amplifier or the noise figure of the amplifier. They both represent the same thing, just in different quantities. That's basically what we will see. So a consequence of this, and this is the important part, it seems strange that you started with some signal. Okay, let's call that signal S. The magnitude of the signal as S. Now, in order to complete the picture, you say that, okay, usually the input, whatever you're sending in, also has some noise on the inside. There's some noise always present in the signal. It could be thermal noise, for example. At the output, you get G times S, and that's the gain of the amplifier. The amplifier doesn't know the difference between signal or noise. For it, both are some kind of signal. It's just we decide what is signal and what is noise. So the output also contains G times N. But now I'm saying that there has to be something else here, some N prime, which I choose to write as G times N prime, which is or let me put it as N sub add, which is often how it is called, added noise. If you now look at the total signal at the input and the output, something very strange happens. So here signal was S, noise was N. So signal to noise ratio was S over N. At the output, signal is now G into S, noise is G into N plus N add. That's why I wrote this as G into N plus add. You see that S over N plus N add is smaller than S over N. So which means that an amplifier actually degrades the signal to noise ratio. It seems to be counterintuitive because the whole purpose of amplifier is to improve the signal to noise ratio. And the reason this looks strange is that we are not considering what happens after the amplifier. Usually there is some detector. And that detector now records that information. It could be a spectrum analyzer or it could be a digitizer. And the reason you actually use an amplifier is that the signal levels you have here are incompatible with the detector because the detector's noise level itself is very high. Which means that this signal is so small that it will be buried in the noise of the detector. So this comes here. This output goes to some detector. What is this noise? This is basically like the ability of the detector to detect very small signals. Right? If it's not able to detect it, which means that there's some minimum level it can detect. So that is sort of like a noise floor. So the purpose of this amplifier is to boost everything so that the signal and the input noise and the noise which is added by the amplifier, they are all above the noise floor or above the ability of the threshold of the detector to be received. So you have to compare these two situations. If I send the signal directly to the detector, I get nothing. So that's basically equivalent to saying I've completely destroyed the signal to noise ratio. I don't get any signal at all. So it goes to 0. But now by adding the amplifier, I've made both the signal and the noise high enough that the detector is able to see it. And the detector's noise now becomes irrelevant because the noise coming from this process itself is much, much higher than the noise of the detector. That's usually the condition in which you want to operate. So the amplifier's property then becomes very crucial in deciding what the signal to noise ratio is going to be like. Okay, so this is why even though the signal to noise ratio seems degraded at the output of the amplifier, if you include the detector, then everything is okay. But this fundamental thing that the amplifier will degrade the noise ratio is that it goes all the way down to quantum mechanics. So how do we characterize this thing? That's what we will discuss in the next 10 minutes and wrap up. Okay. So you start by just thinking about how to connect noise, resistors, and temperature. Okay. So you have actually already seen this in other physics courses. There's something called Nyquist noise or Johnson noise of resistor, right? And this is actually the full quantum version of that the voltage noise across a resistor R in a bandwidth B is given by this function. Okay. This is the full quantum version, which you might not have seen. But when you make the approximation, the classical approximation, which is basically to say that KT is much greater than HF. Right? So what is H here? Planck's constant. F is the frequency at which you're operating. Then this thing simplifies to the usual expression which you might have be familiar with, right? That the voltage noise is proportional to KT R square root. And this is, they also call this as the Rayleigh-James limit, because this is basically when you say H of KT is much greater than HF, which means F is very small, or equivalently wavelength is very large, which is the the Rayleigh-Jeans limit of your Planck's radiation law. Okay. So this allows us to connect temperature and resistor to a level of noise. So you can equivalently use them to represent each other. So if you have this noise being delivered to a matched load. So what is this noise representing? It's basically the noise coming from a resistor of value R. Okay. So I can model that as an ideal noise voltage source Vn, which has this property here. And this is basically and it will have a source impedance of R, because that is the resistor which is creating. Right? This is now the idealized model Vn, which is an ideal voltage source in series with this resistance. And this is the voltage spectral density you will measure at this point. If I now put a matched load here, which is R, then you can calculate that the power delivered per unit bandwidth is basically given by KT. Okay. Because power goes as V square over R, and then there's a factor of 2 here in the voltage division. And then if you run to that number and you get this thing. So this is basically the important result, that power delivered to a matched load, this is noise power, is just KT into bandwidth. Okay, bandwidth matters because this is a white noise we are usually considering. It has uniform spectral density across all frequencies. So the more the bandwidth you consider, the more the absolute power is. So usually you only talk about some finite bandwidth B, and in that the power per unit bandwidth is just KT. And it is this relationship which allows you to equate noise and temperature. And because in microwave frequencies, everything is 50 ohms, source is 50 ohms, load is 50 ohms. So then and you can see that actually the R factors out. It doesn't even come here, but R is fixed in our microwave environment. So when you say that a resistor has a noise which is equivalent to a temperature, basically you're using this idea here. Okay, but it's also the same noise which a resistor will create when it is at that particular temperature. So this allows you to connect noise and temperature in a consistent way. So basically, when you say temperature, you know exactly what noise levels you're talking about. Okay, and that's essentially the model which allows you to make this mapping. So here it's sort of saying what it means. What they're saying that if you had some arbitrary noise source, with some level of noise connected in it, and you say that that is delivering certain power, if you equate that power to kT and bandwidth, you can get an effective temperature. So it's equivalent to having a resistor with that equivalent temperature and the power delivered, so that the power delivered to the matched load would be kT into bandwidth. So this is the mapping. So equivalent temperature is basically the noise divided by K into B. So here B is bandwidth. So this is not only KB, like sometimes we write KB for the Boltzmann constant, right? So this is not that. Okay. Now, how does this finally connect to the idea of characterizing the noise temperature? So this figure basically explains that. So you assume, because there's always an input impedance and an output load for any microwave system. So if we had some input resistor, again, remember for us, it will be always 50 ohms. And we sort of assume that this resistor was at zero temperature, which of course in reality not possible. There's also quantum fluctuations, but we are in the classical limit, which we are saying that, okay, this resistor is not emanating any noise. So in this picture, we are considering an idealized scenario where this noise doesn't exist. Okay, but the output of this is going to have some noise, and that is going to deliver some noise into this resistor. So you transform that into a different picture where you say that what is the temperature of this resistor which would give me the same noise at the output if the amplifier itself was noiseless. Is this part clear? In the first thing, we are taking a noisy amplifier. All amplifiers are noisy. We are saying there is no input noise coming in. This is a hypothetical situation. And then we see how much noise is being delivered to this matched load at the output. We then ask that if the amplifier was noiseless, which means it was not adding its own noise, what is the temperature of the resistor which would give rise to the same amount of noise delivered to this resistor here? This is the mapping which allows you to define the noise temperature of an amplifier. It's a way of taking the amount of noise it's adding, referring it to the input. So remember, it's the noise is at the output. Referring it to the input means that you have to divide it by the gain of the amplifier, and then asking what is the temperature of the equivalent resistor which would give you the same amount of noise. So that is the definition of noise temperature of an amplifier. Sorry?
The amplifier circuit doesn't have resistance.
The amplifier circuit doesn't have a resistance of 50 ohms. It should look like a 50 ohm input on both the input side and the output side. So way to draw that is that so this is a model for an amplifier just from the input and output. So it looks like a resistor for anything that is connected to input, and that resistance should be 50 ohms. And it looks like a voltage source with some resistor in series, and that also has to be 50 ohms. This is the ideal case. Most real amplifiers have, impedances close to 50 ohms, but they are not. So again, in the context of return loss, we measure this as, okay, if it is better than 20 dB, then we know it's close enough to 50 ohms. But usually they are not perfect. They will be slightly mismatched, but not by a lot. Okay, let's see. I'll just take 5 more minutes.
There is a concept of we divide in steps rather than
That's the last thing I'm going to talk about before we stop. So when you want to measure the noise temperature of you have been given an amplifier, how do you figure out how much noise it is adding? So usually you need something whose power or noise power precisely. And one thing, especially for experiments which are happening in cryogenic things, or even if not, is that because of this equivalence of temperature and resistance, temperature and noise, you can use temperature as a source of calibrated noise. Okay, so that's basically what it's showing you here. N1 is the noise at the output of the amplifier when the input resistor is at temperature T1. Okay, so remember what it's saying. The total noise at the output is the noise contributed by the resistor multiplied by gain into bandwidth, plus the noise contributed by the amplifier, which is written as the same temperature of the same equivalent resistor. So this is the total noise you get at the output, right? So here you can measure N1 on your device, on your, say a spectrum analyzer or a power meter. Then you change the temperature of that resistor, and you now have a different T2. So you have a different noise. Since you know T1 and T2, you know exactly what this ratio is, right? But the output will now have this new noise, but added noise is not going to change. The amplifier is still going to add the same noise. Okay. Now there are some caveats here in reality, is because you have to only change the temperature of the resistor, of the input resistor, not that of the amplifier. In some cases, if the amplifier's temperature changes, its noise itself could change. Okay, so that is important to keep in mind here. And now from these two equations, you can actually calculate what TE is, because that's essentially the noise thing you can calculate. And that basically comes from this formula, where this Y is essentially the ratio of these powers. And that's why it's called a Y factor method. By knowing the ratio of these two noise powers for the amplifier with two different temperature measured here, you can calculate the. So usually it's also called, so it's done something like this. You have a hot resistor and a cold resistor, and you switch the input from one to the other, look at the ratio, and you can get. So you need 2 points, but essentially, if you see this is like an equation of a straight line. So sometimes what you do is you plot the noise as a function of temperature, and then you draw a line, and this negative intercept here gives you TE. So if you had, in a cryogenic setup, you can do that by measuring it. Just gives you more data points to extract the noise temperature more precisely. Sometimes instead of using temperature, you actually use a calibrated noise source. So this is some device which you can specify, and it will put out exactly that amount of noise, because it all essentially relies on knowing what this noise level is, right? So you can now have, instead of T1 and T2, you can have two input noise levels, N1 prime and N2 prime, and that will also give you the same results. So normally at room temperature, you can buy these noise sources which are used for calibrating the noise temperature. Otherwise, you'll have to find some way to heat a 50 ohm resistor, or you can use room temperature and liquid nitrogen or ice, for example. But the amount of temperature difference you need depends on how much this noise is. Right? If this noise is very high, then a very small change in the noise level of the input will not give you very accurate measurements. So all of those things make it easier if you have a calibrated noise source for doing that. Okay, so that's how you measure noise temperature. And the last part is got to do with what Aishi was asking, which is, and by the way, there's also a thing called noise figure, which is just related to the noise temperature in this way. It's a ratio which is of the temperature of the noise temperature to some standard temperature, which is usually 300 Kelvin. And then you give that in dB. Okay. So it's this part about how noise changes when you combine multiple amplifiers. Okay. So this is very important because often in any experimental setup, you might have many amplifiers of different types. So it's easy to see that the total gain of the combined system is just the sum of all the gains, in log units, or the product of all the gains. But how do you think about the noise? So let me call the first one as gain G1 and noise temperature as Tn1. Second one has gain G2, noise temperature Tn2. Okay. The output here is going to be whatever the input is, plus I'm going to forget the input part. I'm going to only write down the noise part. Okay. So the output noise here is G K Tn1 into bandwidth. Right? That's the noise which is going to come from the amplifier. If I now look at the output of this guy, this noise is going as input to this amplifier. So the first term you're going to get, so this is G1, is this multiplied by the gain of this amplifier. So you have G2, G1, K, Tn1, B, plus the noise added by this amplifier, which is G2, K, Tn, This is clear. It's just pretty straightforward. This puts out this much noise. This guy amplifies that noise, and that is this term, but adds its own noise, which is this term. So the total noise at the output is this much. Now, if I want to treat this two amplifier system as one single amplifier, I need to know, in order to define this amplifier, I need to know its gain and I need to know its noise temperature, right? So let's call that G and Tn. G is obvious because G is just going to be the product of these two gains. So assuming, so this here, G's are all power gains in linear units, right? That's why I'm writing like this. So G is just G1 into G2. And if Tn is the new noise temperature, hypothetical or the noise of this new amplifier is going to be G into Tn into B, which is equal to G1 into G2 into Tn into B. And this has to be equal to this, right? So I can divide everything by G1, G2, B. So then I get, so this is equal to this. Tn. So G1, G2, B means these two things will all go. In fact, I can this K also. So I can kill the K. So this will completely kill all of these terms. Right? So this is Tn1 plus in this term there is G2, K and B. So those will get cancelled, but G1 will remain. So I get Tn 2 divided by G1. So what it's telling you is that when you have two amplifiers cascaded like this, the noise temperature of the final combined amplifier is mostly the noise temperature of the first amplifier. Why I say mostly? Because I'm assuming that G's are large, right? Otherwise, an amplifier is useless if the gain is not very big. But the noise temperature of the second stage is reduced by the gain of the first stage. Intuitively, it makes sense because you can see that whatever was here, this has been amplified by a factor of G. So if you go in the reverse direction, the equivalent noise of this input from this perspective, because this is what we're trying to find out, right? What is the temperature, the noise temperature of this combined amplifier is the effective noise we attribute to this resistor. So in the reverse direction, all the noises above are going to be reduced by the gain factor. So it means that if you have a chain of amplifiers, you want to put your best amplifier. Best here means lowest noise, and ideally it should have high gain as well. Because if the first amplifier has low noise and high gain, the total noise of the system will be as close as possible to the first. So you can actually create a system where the noise of the entire system is only set by this one, and the rest only sort of contaminated by a small amount. And this is very crucial to sort of know, especially in cryogenic experiments, because usually when we have a series of amplifiers, the first amplifier is at the cryogenic level, and that will have the lowest noise. And then we can put worse and worse amplifiers. But it's important to have large gain as well. So it also actually tells you, the other way to think about it is that once you have some amplifier here, it tells you how good of an amplifier do you need here in order to maintain the noise as much as possible, right? Basically, it means that the noise temperature of this guy needs to be small compared to gain times the noise temperature of the first guy, because that's the noise which is anyway coming in. So if the amplified noise of the first stage is small compared to the input noise of the second stage, then you will not. So this will work for any number of stages. What will keep happening is that, so Tn1, Tn2 plus G1 plus Tn3 over G1, G2, and so on and so forth. So as you go further and further away, the noise becomes less and less important. So that's what's discussed in this part of this as well. Okay, so I think we'll stop there. Any questions about this? So as I said, there'll be one combined assignment, or I'll split it into two, which is now you can submit it on basically on the day of the exam or before. And the exam will happen on Jan 16th, Monday. Okay. It will consist predominantly of problems which you'll eventually have to implement in microwave office. Okay. So before that, we should make sure that all of you have some way of accessing the microwave office software. I guess there are about 8 or 9 of you who are taking the course for credit. So only those people are giving the exams. The others don't have to. And I'm not going to grade the other exams as well.
What is the mode of exam? Can it bring in note or?
I'll tell you what you can bring. It's sort of an equivalent of an open book type of exam only. But I'll tell you, I'll give those instructions much before, maybe a week before the exam. So it will be a sort of a slightly longish thing will happen in class. And then I'll also talk to you individually about some subset of that problem you have done. So that's how the exam will be conducted. Okay. So I don't know if Jan 16th are the lectures already starting. Is that really might be the first day of lectures, right? When is the term supposed to start? That's the DP1 submission, right? But it's possible 16th might still be the first day of lectures. Anyway, I'll block a room and then I'll inform you. And assignments will come to you today.